We're going to look at this question about a lift, and it's about, in particular, it's about a passenger in a lift and the forces that are involved when the lift is moving at a constant speed, when it's accelerating upwards or when it's accelerating downwards. So I like to really simplify this down. If you've got a lift and you've imagined you've got a passenger in it, I'm just going to draw my passenger as a wee box, then I like to consider, I consider my lift as a whole thing, in which case you've got a tension, and then you've got the weight, which is the weight of the lift, big mg, and you've also got the weight of the passenger, which is small mg. That's what you've got. So if you consider the system as a whole, that's what you've got. And then if it's just moving, if you've got your lift moving as one body, then you've got your tension going upwards equals your tension going upwards equals your mg plus your lowercase mg going downwards. That's what you've got if it is just going at a constant speed. If it's accelerating upwards, then you're going to have to use F equals ma. So in this example here, it's going upwards. T minus big mg minus small mg will be equal to my total mass, which is big M plus small m, times my acceleration. Okay, if it then was going downwards, so if we change this situation, and it's now going downwards, let's see how this changes round. And if it's accelerating downwards, that's what you would have. And downwards, you'd have big M plus small m. The force is going downwards. Force going upwards is T, and that equals my mass, which is still big M plus small m, times my acceleration. So that would be your initial setup. So you just substitute in whatever the values are. But for us, our diagram here is different because we're just looking in this question at a man. So let's read the question and see how our example is different. So it says the motion of a lift when ascending from rest is in 3 stages. So first, it accelerates at 1 meters per second until it reaches a certain velocity. It then maintains this velocity for a period of time, after which it slows with a retardation, so that's deceleration, of 1.2 meters per second squared until it comes to rest. Find the reaction between the floor on the lift and the passenger of mass 100 kilograms during each of these 3 stages. Okay, right, let's look at our diagram. And I'm going to draw a wee man here, just so that's really clear. You've got a wee man, all right? Don't be intimidated by my fantastic artwork skills here. You've got a wee man standing in this lift. Here he is. And he's standing in a lift. If this man is in a lift, the tension in the cable is not what's getting him going, okay? Because he's not holding on to a cable. So it's not like his wee arms here are up here and he's holding on to this cable. That is not the case at all. Okay, so we get rid of those, and what's getting this man moving isn't anything to do with tension of the cable, really. It's the reaction from the floor. So you've got a reaction from the floor, and he's got his weight, and we'll call it, in this case, he was 100. If he wasn't 100, you didn't know, it would be mg. But that really is what's going on. So in the first stage, that's what we've got. And there's constant acceleration, is it? First stage, it accelerates at 1 meters per second squared. So going upwards at 1 meter per second squared. So we're going to use F equals ma. So he accelerates. Acceleration is happening. So force equals mass times acceleration. My force upwards is R minus my mass, which is 100g. And 100, and then minus my weight, which is 100g. My mass is 100 and my acceleration is 1. So that means R is equal to 100. Bring that 100g across plus 100g. So R works out to be, and I'm assuming my g is 9.8 here. So I'm just doing that on my calculator, 100 plus 100 times 9.8. And my R works out to be 1080 newtons. Okay, my second stage, since this is such a good diagram, I'm going to copy this. And for my second stage in, I would have the same diagram almost. In the second stage, he's going at a constant speed. All right. So it says here in the second stage, first stage it accelerates. So that was my first stage. He accelerates at 1 meter per second until he reaches a certain velocity. It then maintains this velocity for a period of time. Okay, and then the last one, after which it slows with a retardation of 1.2 until it comes to rest. Okay, so you have 3 stages. So we're in the blue stage here. so it's going at a constant velocity. So if a constant velocity, so it's not a double-headed arrow, it's just a single-headed arrow, and that means you resolve vertically, and the force up equals your force down. No acceleration, so that's all you have. So that's just going to be 100 times 9.8, and that is obviously going to be just 980 newtons. Okay, in my third stage, let's just copy this beautiful diagram again. In my third stage then, we are going to have, so it's going to be same diagram again, but this is he's now slowing down. So this is our third stage. He's going this direction, but he is slowing down. So I'm just going to call that A, and we're going to resolve vertically, but we're using F equals ma. If there's acceleration, you use F equals ma. So what's going up is my R. What's going against it is my 100g, and that's equal to my mass times my acceleration. I think we know our retardation was 1.2. So that means he's slowing down, so that my acceleration is minus 1.2. So it's my mass, sorry, let's do that again. My force upwards is my R, going against that is 100g, that's his weight, and my mass is 100. My acceleration is minus 1.2, which means R is equal to, that's going to be 100 times minus 1.2, and then plus 100 times the g. So remember your g is 9.8, so 100 times 9.8, and then add your 100 times 1.2 minus 1.2, and that should give you this time 860 newtons. So have a look at this and see if this even makes sense. So the first one, for him to accelerate upwards, my R worked out to be, and my R worked out to be 1,800. So to get me accelerating upwards, it's a pretty big force. Once I'm going at a constant speed, you can see this one, it was less force. And the last one, when I'm slowing down, even less force again. So that would make perfect sense to me. So you can see the three different scenarios. So to me, that makes a lot of sense.